So in section 3.3, we are talking about cardinality and pigeonhole principle. First, let's review a couple of notions from your previous math classes. And these are about the function, or sometimes we say mapping. Very often we say mapping or function. So when we have a mapping f from A to B, oops, I forgot to put the title, 3.3 cardinalities and pigeonhole principle. So let's recall what is a function from a set A into set B. Do you remember definition from pre-calculus, algebra, or wherever you got it? What is that?
For every A, there's a unique B. No, at least one B. But for every B, there's only one A.
Yes. So generally, in set theory, although functions we usually imagine like this. This is the best intuition about function, but it's not so nice kind of to describe mathematical language. I always think of this. So here is my function label. Function is labeled f, not f of x. F of x is usually the number. So the name of the function is f. I put that on my machine, and then what? I feed input, and that input is from where? From A. And I get output, which is from where? From B. Okay? And there is a rule that says what? That for every input, I only get what? One output. Now, in this setting of set theory, here is an easy way to describe function. Like, do we often describe function as a set of pairs? You pair input and an output, agree? So we'll say the following. F is a subset of A cross B. Because why? Because A cross B has couples, do you agree? First component is from where? And second component is what? B. But not every subset, because I want that property what? That for every F is subset of A cross B, and what else? For every A from A, there exists only one, and maybe I never show you this symbol. Usually we say there exists with exclamation mark. There's only one B from B such that AB belongs to F. And this is the definition of function in purely set theoretical language. But you can say, whoa, we never studied there exists only one. But we played with that in homework problems. That's exactly why we played. If you don't like using extended language, you can say the following. F is subset of A cross B. And what else? For every A from B, from A, and for every B and C from B, if A and B belong to F, and A and C belongs to F, what must happen? If A has image B and A has image C, those images must be what? The same. B equals C, exactly. Here is the way to say this if you don't want extended language. So this is a very precise definition of a function. There are no stories, there are no pictures. Here it is, function is a set with the prescribed properties. You lose a little bit of intuition that you see here in application, but you have a very precise definition. Everything is quantifiers and sets, so nothing really ambiguous there. And you can write a program about this, and your program would recognize function and distinguish them from something that's not function, and so on and so on. So this is definition of function. But what else? When do we say that function is a one-to-one, we say?
There's only one
Yes, so every input has its own output, so there's no output sharing because otherwise so f is 1 to 1 means what? For every a1 and for every a and a1 and for every a2, if f of a1 equals, if they have the same image, they must be same themselves. So, because otherwise function can have two different inputs producing the same output, but if function is 1 to 1, that's not allowed. By the way, very often we write this in a contraposition. So how would contraposition, good exercise, what we did. Let's do the contraposition. If A1 is different from A2, then what? Is not equal to F of A2. Two different inputs produce two different outputs. So that's when we say that function is 1 to 1. And then one more thing, that one you probably haven't seen very often before. When do we say that function is onto?
If it's the same.
Every output has an input.
Exactly, every output is being produced, every output is being used. So for every B from B, there exists A from A, such that f of A equals B. So you don't have some unproduced elements from the codomain.
What is that called again? F is outlet?
Onto.
Why do you have that Jacobian symbol?
No, it's not Jacobian. Where?
In the middle of your last line, after B, you said.
Exists. No, this is exist. Existential quantifier.
It looks like when you would write it in
Yeah, okay. Context dependent. All right.
But you're context for Calc 3.
No, yeah, no, true. Sorry. All right. So these are three most famous kind of definitions about the functions. And actually, they are very important when we count the objects. And that's interesting, where concept of cardinality comes up. So here it is. Let's look at this set here. How many objects do you see here? Yes, just on the plate. And usually, how do we count? How do we say that there are three of them? Particularly when you look how kids do that, they touch objects, say 1, 2, 3, and when they are touching, they are keeping track that such an object exists, and they also want to keep track that they're not coming back and counting something twice or something like that. It's very hard to count when objects are moving. You know how that goes. So, generally, mathematicians came to an idea how to describe the size of a set by doing the following. This touching is actually, you are kind of making a function between natural numbers, which are what you say, and the object. So when I touch this, I say 1. So that means f of 1 is my glasses frame. F of 2 is what? When I say 2, f of 2 is what? Bigger chalk, and then f of 3 is this one. So generally, I have like a counting is mapping. So you say the following, 1, 2, 3, and then first one, and then first chalk, shorter chalk. And then what is important about this mapping? Is this a function, yes or no? And what is important about that function? Is it 1 to 1, yes or no? Yes, and it's also onto. That means I counted everything, and I never counted something twice, to put the same number twice on the same object. So that means F is the mapping between certain set of numbers, and I call that N3. Why N3? Because it's a set of what first? 3 numbers, and that object A. If I have that, then I will say that cardinality of A, usually we put absolute value, but a double one, we say cardinality equals 3. And then the same thing is, some sets might have more elements than 3, and so on. Of course, besides finite sets, we also have infinite sets that you can never count completely. What is one of them? Natural numbers. So natural numbers, n is infinite. Why? Because you can never, because finite set we always say are those that could be counted with n3, n7, nk's for certain k. Once you stop counting and say I'm done counting, if you are never done counting, that set is called infinite. So one of them is a natural number. Do you know another infinite set? Real numbers. So real is infinite. All right, and integers, rational numbers. And then it's interesting. Is there, so this is really a little bit off our topic, but I cannot resist because this is what I've been doing all my life. So how do you compare different versions of infinity? Do you think that there are more natural numbers or more integers? No, equally. Why? I'll make a counting function between two of them. How? Here it is. Here is 1, 2, 3, 4. Can I count all integers? Yes. 1 will count itself. 2 will count -1. 3 will count what? 2, and 4 will count what? -2. 5 will count 3, 6 will count -3, 7 will count. Do you understand the pattern? Will I cover all of them, yes or no? So do I have bijection? So are they of equal size? Yes, they are. So this is of equal size as this is equal size of this. Can I count all reals? The answer is no. That's a famous counter-diagonalization process that says this can never count reals. I can show you that once, maybe next time if you care, or stop by my office. Yes?
So is this where the terms countably infinite and uncountably?
Exactly. This is countably infinite, and this is uncountably infinite. And then those are all called countably. The name for that is Aleph 0. So that's from Hebrew. And this one is called C, continuum. So we know that this is more than this. So Aleph 0 is less than C. And then, this is one of the big moments in the history of mathematics. In year 1900, David Hilbert, greatest mathematician of that time, German mathematician, in the beginning of the century, asked the math world questions that should be answered in 20th century. And he asked 23 questions. Most of them happened to be big breakthroughs in mathematics. So people were doing them, for tens of years or decades. Or some of them were answered in 1920s, some of them in 50s, some of them were never answered. They're still open. A few of them were easy, though, But number one on the list is this one. Is there a set that has more element than natural numbers and less element that's continuum? Is there a cardinality that's between them? So now, you know what's the answer that we got 114 years later?
No. W?
Could be both. Which is probably surprising for your experience in mathematics. Actually, what happens is, in 1930s, Gödel showed that actually there might be that there is nobody in. And 50 years ago, in 1963, American Cohen showed that actually it might be that such a set does exist. What we say, both answers are consistent with our knowledge, and our experience will never be rich enough to challenge any of the answers. So there are alternative mathematics developing. This is famous continuum hypothesis. Continuum hypothesis. So this is first problem on the Hilbert list. And as I said, now we consider that as a settled. So now we say either way. So There are versions of mathematics that accept continuum hypothesis being true or being false, and different versions of it. You can read more about it. As computer scientists, you don't need to worry about it at all, because you work most often with finite cardinalities, and that's what, this is just a little digression. So we want to see when our sets could be counted or not.
See the guy that made
Yes.
the Hubert's Hotel?
What's that?
See the guy that made the Hubert's Hotel analogy with the infinite rooms and infinite.
Exactly, yes.
Oh my God.
Yeah. So yes, that's with infinite room is actually this mapping here. Yeah. And it's interesting. Rational numbers are completely dense inside real numbers, but still they are much small. There's a much smaller number of rational numbers than reals. But going back to the finite numbers, I wanted you at least to hear. I rarely ask. I don't know even ever if I ask on the exam, but I'm not saying I will not. I want you at least to hear about pigeonhole principle, because it's sometimes used, and it's fairly easy thing, and it's interesting principle, and I don't want you to be surprised when you hear it somewhere in one of your computer science classes. So what is the pigeonhole principle? It's so simple that it's unbelievable that it even has a name assigned to it. But as I said, in the middle of something, you go into that part of argument, and then you just call it and say, by pigeonhole principle, and you at least you need to understand what it means. So what is pigeonhole principle? Very simple. You have 10 pigeons and 9 holes. And you want to put all the pigeons in the hole, so no one stays outside. What can you conclude from these numbers?
One hole is 2 pigeons.
At least 2 pigeons, yes. So that's it. So if you have a mapping, and that's pigeonhole principle. It says the following. If A and B are finite sets, so pigeonhole principle, says the following. Pigeonhole principle. Let F be mapping or function from A to B. Be careful. Both A and B must be what? Finite. A and B finite. And what else? Cardinality of A is strictly greater than cardinality of B. That means A are pigeons and B are holes. So what can we conclude? That actually F is not one-to-one. Because pigeons are inputs and holes are outputs, so you must have output sharing. Is that what it is? F is not one-to-one. That means there exists A1 and there exists A2 from A, such that what? A1 and A2 are not the same, but their hole is the same. So this is a pigeonhole principle. Is that clear to everybody? All right. So principle is common sense, and actually we can also make some proof by induction or something like that. If you really want absolutely rigorous proof. There is a more general version. And I'm not going to record it precisely. You're having problems reading what I wrote. Is that what it is? Okay. So if A and B are finite, cardinality of A is greater than cardinality of B, strictly bigger, then F is not one-to-one, which means the following. There exists A1 and there exists A2 from A, such that they are not equal. A1 is not the same as A2. And what else? F of A1 equals F of A2. Two different inputs share the same output. More general version. What if we have the following? That cardinality of A, the same, everything is the same, is not only greater than B, but it's greater than K times B. Like cardinality of A exceeds 3 times more than the houses. What can you conclude?
It's the same.
If you have 31 pigeons and 10 houses,
One house must have 4
Exactly. So not only 2, but generally what? If you put 3 pigeons in each house, that's 30, do you agree? And then that remaining one must be the 4th one somewhere. So if cardinality of A exceeds K times cardinality of B, then how many of pigeons now we have? Not only 2, but how many K? Plus 1. There exists A1, there exists A2, there exists AK plus 1, such that f of A1 equals equals f of AK plus 1, and they are all distinct.
Sort of a ceiling function almost.
Yes, you can think of it that. Yeah. You're right.
What is if you put whatever?
And just a second, let me record this. A1 different from AK plus 1. So this is called generalized pigeonhole principle, and this is just standard pigeonhole principle. Yes?
But what is if whatever, 31 pigeons all going to go in the first hole?
That's it, I have 31. So this says I have at
So that
least
means
4.
At least.
But that's what I said exists. So if I have 31, I also have 5. So I'm not saying there exists exactly. No. But just at least. All right. Does this sound like something worth discussing too much? Probably not. But here's what's big about it. You will see a few problems where actually the whole thing is to interestingly design the appropriate function and then make the appropriate conclusion. So it's more like, at the end you just call this principle, which is obviously common sense, but we'll see after the break a few situations where this naturally arises and how to design this function skillfully. So that's what we'll do after the break. Let's take a break. We continue at 38. Did we have the lights on this side?
There's supposed to be just a red.
Just red?
Red over here, I believe.
No, green on the, yeah, green on the
Green on the side. Oh, good.